Welcome to week 5 of Nino and Calandra's college algebra cohort. Graphing exponential functions. An exponential function is a function that has a variable expression as an exponent. So far, we've been looking mainly at polynomials where you have a variable raised to a numerical power. However, for an exponential function, we're now going to have numbers as the base and exponents that have variables in them. The basic exponential function is of the form y is equal to some number raised to the x power. So b, our base, can be any real number. And the graph of such an exponential function will look one of two ways depending on the value of that base b. Well, the first way it could look is an increasing function. So this is the graph of y equals b to the x if the base is a number that's bigger than 1. So if the base is bigger than 1, then you'll have a graph that is increasing. So remember that what it means for a graph to increase is if it's rising as you move from left to right. And we see that this graph is rising as we go from left to right. Now this graph has a y-intercept, and remember to find the y-intercept, you set your x equal to 0. If I plug 0 in for x, we're going to have b, which is just a number, raised to the 0 power. And anything raised to the 0 power is equal to 1. So we'll have a y-intercept at the point 0, 1. The domain of this function, so remember the domain are all the values you can plug in for x. Well, we can raise a number to any power. So the domain is going to be all real numbers from negative infinity to positive infinity. And you can see that from your graph. Any x value that you pick, there will be a corresponding y value on the graph. Now the range, on the other hand, the range are the y values that we have, and notice that the graph does not go below the x-axis. So the smallest value that we can have for y is 0. However, there's no number that I can plug in for x that when I raise a number to that power will give me 0. So 0 is not included. Okay, so keep in mind that base, b, is some number bigger than 1. So you can visualize, for example, 2 to the x power. Is there any number that you can plug in for x that's going to make this y equal to 0? And the answer is no. The only number you might think about is, well, what if we plug 0 in for x? Well, anything to the 0 power is 1. So there's no possible number or x value that's going to make our y equal to 0. So that's why 0 is not included. And then from the graph we see that the y values, anything bigger than 0 is going to have a corresponding point on the graph. So our range will be from 0 to 1. We have a horizontal asymptote. So a horizontal asymptote is a horizontal line that your graph gets infinitely close to without crossing after a certain point. So the x-axis is a horizontal asymptote for this function, and the equation of that horizontal line is y equal to 0. There is no vertical asymptote for this function. Right, well, that's the first possibility of what b to the x would look like. The second possibility is going to be a decreasing function, and that's if the number b is a fraction that's between 0 and 1. So if it's between 0 and 1, we'll end up with this decreasing graph. So if we look at the y-intercept, just like we did with the other graph, y-intercept means we're substituting 0 in place of x. If we do that, anything to the 0 power is equal to 1, so we still have that same y-intercept at 0, 1. The domain, we can use any x value and get a corresponding y value, so it will still be all real numbers. The range, again, starts at 0, not including it, and goes to infinity. Any y value that you pick bigger than 0 will have a corresponding point on the graph. That's what we mean by the range. We will have the same horizontal asymptote. So notice that the graph gets closer and closer to that horizontal line without ever crossing it. So the equation of that horizontal line is still y equals 0. And again, there's no vertical asymptote. So let's use this generalization of what the graph of b to the x looks like in order to sketch the following functions. So the first function that we're looking at is y equals 1/3 to the x power. Okay, well, I see this as an exponential function. I have a number being raised to a variable exponent. So I need to look at what my base is, and I know that 1/3 is a number that's between 0 and 1. Therefore, this is going to be the decreasing graph. So if you remember those generalizations that we just went over, what the graphs will look like based on the value of b, we have enough information to be able to sketch it and to tell the domain and range. So this will be a decreasing graph that goes through the point 0, 1. The domain will be all real numbers, and the range, the y values, will be 0, not including it, to infinity. And that's it. Going on to part B, we have y is equal to 3 raised to the negative x power. So we're going to look at our base of 3. Since 3 is a number that's bigger than 1, that tells me that this is going to be an increasing exponential function. Now this is just looking at if we had 3 to the x power. Okay, so I'm going to draw that in as a dotted line because notice we don't have 3 to the x. We have 3 to the negative x. Okay, so 3 to the x would be an increasing graph. Well, what do we do for that negative x? This is when we go back to what we learned earlier about transformations. So that negative x is going to cause our graph to be reflected around the y-axis. So we're going to reflect our dotted graph around the y-axis. So if we do that, the point 0, 1 will still be there. We're just going to have a mirror image, so our graph will be coming down like this. So we still have that point 0, 1. Our domain remains the same from negative to positive infinity, and our graph continues to approach a y value of 0, not including it, so the range will be from 0 to infinity.